Hello, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we're going to do a kind of X-ray on reality. We'll take the things you touch every day, paper, hair, water, even your own skin, and peel them down, layer by layer, until we reach the level where matter stops looking like matter and starts looking like organized nothing. Settle in, dim the lights, and get cozy. But before you do that, take a moment to like the video and subscribe to the channel. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world, and I appreciate you for being here. When we talk about atoms, we tend to use the same word we use for crumbs and buttons and smartphone screws. Small. That's already the first mistake. Atoms don't live on the same scale as anything you handle. They don't even live on the same scale as the things you can barely see, like dust, or a cell, or a grain of pollen. Atoms live several steps below that, in a size regime the human brain has no practice with. So let's build that size ladder properly. Start with something your body understands. 1 meter. That's from the floor to the kitchen counter, or from your shoulder to your hand. Cut that into 10 pieces, and you get 10 centimeters, the width of a book. Cut a centimeter into 10, and you get 1 millimeter, the thickness of a credit card or the line on a school ruler. Up to here, no problem. Now cut that millimeter into 1,000 pieces. Each of those pieces is a micrometer, 1/1,000,000th of a meter, 10 to the -6 meters. That's where red blood cells live, about 7 micrometers. Where a human hair's thickness lives, about 70 micrometers. Where fine dust and some bacteria live. You can't see these clearly, but at least they're connected to things you know. Hair, dust, cells. Now cut the micrometer into 1,000 again. That gives you the nanometer, 1/1000th of a meter, 10 to the -9th meters. This is the playground of viruses, big biological molecules, and the features on computer chips. If you've ever heard 7 nanometer process in tech, that's this scale. And atoms sit at about 0.1 nanometers, 1/10th of a nanometer, or 1 times 10 to the -10th meters. So from 1 meter to an atom, you have divided by 10 3 times to get to a millimeter, then by 1,000, then by 1,000, then by 10 again. Multiply those, 1,000 times 1,000 times 1,000 times 10 equals 10 billion. 10 billion. That is the gap between my arm and one atom. If you tried to mark the width of an atom on a 1 meter stick to scale, you couldn't. You'd have to slice it into 10 billion pieces and point at one sliver. That's why you have never seen an atom with your eyes, and never will. Our senses drop out of the game way, way earlier, long before the nanometer, let alone the 10th of a nanometer. And this is just the start. Because inside that already outrageous smallness, the atom itself is mostly empty, and the part with almost all the mass is another 100,000 times smaller than the atom as a whole. So when people say atoms are tiny, what they should say is, atoms are 10 billion times smaller than your normal world, and inside them, the real stuff is another 100,000 times smaller again. That's the scale we're dealing with tonight. Not small, but so far below your experience that we need new words and a calm pace to make it real. Now that we've built the staircase down to the atomic level, we need to make it stick by putting atoms right next to everyday objects. Numbers only hit when they have neighbors. Let's start with something you've seen 1,000 times, a sheet of printer paper. A normal sheet is about 0.1 millimeters thick. That's 1 times 10 to the -4 meters. An average atom is about 1 times 10 to the negative 10th meters. If you divide 10 to the power of negative 4 by 10 to the power of negative 10, you get 10 to the power of 6, which is 1 million. So a sheet of paper is about 1 million atoms thick. Not a lot, not thousands, but a clean million atomic layers stacked up. That's what your fingers are feeling when they pinch paper. A million layers of mostly empty atoms that, together, act like a flat surface. Now swap the paper for a human hair. A typical hair is about 70 micrometers across, which is 70 times 10 to the minus 6 meters. Divide that by 10 to the power of negative 10, and you get 7 times 10 to the power of 5, 700,000. That means you could line up around 700,000 atoms across the width of a single hair you barely notice in the sink. Take a grain of table salt, around half a millimeter, 5 times 10 to the power of minus 4 meters. Divide by 10 to the power of negative 10, and you get 5 million. 5 million atoms across a grain you flick off the table. Even a speck of dust floating in the sunlight, maybe 10 micrometers across, is still 100,000 atoms wide. This is the first big lesson. Even things we call tiny are still absolutely enormous on the atomic scale. But we can go smaller in daily life. Think about the nail on your finger. It grows about 1 millimeter a week. 1 millimeter is 1 times 10 to the negative 3rd meters. Divide that by 10 to the power of negative 10, and you get 10 million. So in one normal week, without doing anything, your body quietly built up a nail layer 10 million atoms thick. You didn't feel it because our nerves don't report at that resolution, but the construction was happening. Your skin does it too. New cells pushing up, each cell full of molecules, each molecule full of atoms, all laid down in neat stacks thousands of layers deep. Even your breath is full of atomic scale counts. A single breath of air contains on the order of 10 to the power of 22 molecules. That's 10,000 billion billion. And every one of those molecules is made from a few atoms. You breathe in more atoms in one inhale than there are grains of sand on all Earth's beaches. That's what makes the atomic scale so different from our normal one. The unit is unbelievably small, so the counts are unbelievably large. A spoonful of water? About 10 to the 24th power molecules, call it a septillion. Your body? About 10 to the power of 27 atoms. A glass bottle, a phone, a book. All of them are just stacks and stacks and stacks of 10 to the minus 10 meter building blocks. And it all looks smooth because our eyes and hands average over millions of layers at once. When you drag your finger over wood, you aren't feeling individual atoms. You're feeling the collective behavior of a million atom-thick surface. When you snap a pencil, you aren't breaking a few bonds. You're breaking astronomically many atomic bonds in one go. So when we say the actual scale of atoms compared to everyday things, this is what we mean. A hair is hundreds of thousands of atoms across. Paper is 1 million atoms thick. Dust is 100,000 atoms wide. Your nail grows 10 million atoms in a week. And you, the big, complicated human, are just a pile of those layers pretending to be solid. Here's the part that always sounds like a magician's trick. After everything we just said about atoms being ridiculously small and stacked in the millions inside everyday objects, the atom itself is mostly empty space. Not kind of empty, not there are some gaps. We're talking about a structure where almost all the mass is crammed into a tiny point in the center, and the rest is a big bubble of "you're not allowed in here" created by electrons. The numbers are brutal. A typical atom is about 1 times 10 to the negative 10th meters across. The nucleus at its center, the part made of protons and neutrons where almost all the mass lives, is about 1 times 10 to the negative 15th meters. That is a factor of 100,000. To make that less abstract, grab the stadium picture. Blow an atom up until it's the size of a huge football stadium, one of those big bowl-shaped ones. The outermost seats, the roof line, the far stands. That's where the electron cloud lives. Not as tiny marbles, but as a fuzzy zone where the electrons are allowed to exist. Now put the nucleus in. It is not a boulder, not a car, not even a basketball. It's a pea sitting in the exact middle of the field. Everything else in that entire stadium is, in terms of real matter, empty. That's not poetry. That's what Rutherford's famous gold foil experiment told us. He fired positively charged particles at thin gold foil and expected them to drift through if atoms were smeared blobs. Most of them did go straight through, because they went through the empty stadium. But every once in a while, one of those particles hit the pea, the tiny, dense, positively charged nucleus, and bounced hard. That's how we found out the atom has a tiny, heavy center and a whole lot of nothing around it. Now you should be asking the obvious question. If atoms are stadiums with peas in the middle, why can't my hand go through the table? Because empty doesn't mean available. That stadium volume is full of electric fields and of the quantum "no, you can't stand there" rules that electrons follow. Electrons are negatively charged. The electrons in your hand and the electrons in the table repel each other. As soon as you push your hand toward the table, those electron clouds start to overlap, and the repulsion shoots up extremely fast. You never get anywhere near the nuclei, but you hit a force wall. Your nerves report that force as solid. So what you feel as hardness is actually atoms refusing to let their electron clouds occupy the same region of space. It's like trying to push two magnets together the wrong way. They never touch, but they resist so strongly it feels like a collision. And now combine that with the everyday numbers from Act 2. A sheet of paper is 1,000,000 of these mostly empty atoms thick. A hair is 700,000 of them across. A grain of salt is 5,000,000 of them across. Each atom mostly space, each with a P in the middle, and still the whole thing sits in your hand like a solid, normal object. That's the real magic of the atomic scale. Emptiness plus outrageous repetition equals matter. If you could somehow remove all the empty space inside the atoms in your body, squeeze every electron cloud down onto every nucleus without changing the mass, you'd be the same weight but smaller than a grain of rice. You'd be terrifyingly dense. But we don't live like that. We live in a universe where matter is mostly arranged space, held open by electric forces, tiled trillions of times until it becomes wood, metal, water, skin. So whenever you hear atoms are mostly empty, don't shrug it off. Remember the stadium, remember the P, remember the 1,000,000 atom sheet of paper. And remember that what you call solid is just organized emptiness doing its job. To really lock this in, let's walk from your world to the atom's world again, but this time we'll park real objects on each step so you can feel how far down atoms live. Start with 1 meter, door handle height, guitar length, your arm. That's home base. Go down to 10 centimeters, the width of your hand, a phone. Drop to 1 centimeter, the thickness of your little finger. Down again to 1 millimeter, the thickness of a credit card or a grain of coarse sugar. Up to this point, your eyes are happy. You can see all of this. Now things start disappearing. Take that millimeter and divide it by 10, 0.1 millimeters. That's about the thickness of a human hair, and you can just about see it, but not in detail. Go another 10 down, 0.01 millimeters or 10 micrometers. Now you're in dust and fine pollen territory. A red blood cell sits around 7 micrometers. A human cell might be 10 to 30 micrometers. You need a microscope now. Go down again to 1 micrometer. Bacteria, fine smoke, tiny fibers. At this point, to your eyes, everything is just too small, but the atom is nowhere near here yet. Now divide the micrometer by 1,000. That gets you to 1 nanometer. This is the world of viruses, of machine-made nanostructures, of the thickness of cell membranes. If I said this protein is 5 nanometers across, that would make sense in biology. And the atom is 1/10 of even that, 0.1 nanometers. So from a red blood cell at 7 micrometers to an atom at 0.1 nanometers, you have gone from 7 times 10 to the -6 meters down to 1 times 10 to the -9 meters, 10 to the -10th meters. A factor of 70,000. A red blood cell, already invisible without help, is 70,000 atoms across. And we can push the ladder even more to blow it out. Inside the atom, the nucleus is 1 times 10 to the -15th meters. So from your arm, 1 meter, to the atom, 10 to the power of -10 meters, is 10 billion. From the atom, 10 to the power of -10 meters, to the nucleus, 10 to the power of -15 meters, is another 100,000. Multiply those, and you get 1,000,000 billion. That's how many times smaller the nucleus is than you. And yet the nucleus holds almost all the mass. That's like saying you're looking at a city that seems to be full of buildings, but actually the whole city's weight is sitting in one tiny bunker under the town square. The rest is corridors of empty but restricted space. Now let's put this next to stuff you literally wore today. Your t-shirt fibers. Cotton fibers are around 15 to 20 micrometers wide. That's 150 to 200 times bigger than a bacterium and about 150,000 to 200,000 atoms across. Your phone screen? The pixels are maybe 50 to 100 micrometers wide, so 500,000 to 1,000,000 atoms across. Even the scratch on your phone, that hairline you can barely see, is thousands of atoms wide. So when we say actual scale of atoms compared to everyday things, we are not joking. Everything you own is absurdly thick in atomic layers. A thin layer of paint, 30 micrometers, 300,000 atoms thick. A human fingerprint ridge, maybe 100 micrometers. 1,000,000 atoms high. Even the oil on your skin, that glossy sheen, is made of molecules that are themselves chains of atoms stacked and folded a few nanometers thick. Your whole visible world is millions of atoms thick, minimum. That's why you never saw an atom. You live on top of a mountain of them and mistake the mountain for the grain. Now that we've got the size in place, let's flip the problem and ask the other question. If atoms are that small, how many of them does it take to make ordinary things? This is where the numbers stop sounding like counting and start sounding like cosmic statistics. Chemists use a shortcut called a mole. It's just a big bucket for counting particles. 1 mole is 6.022 times 10 to the 23rd power of something. Think of it like saying a dozen, except instead of 12, it's 602,200 quadrillion. Why so big? Because atoms are so small that if we didn't group them like this, we would be writing pages of zeros for every spoonful of anything. Take water. 1 mole of water weighs about 18 grams. That's not a lot, a mouthful. But in that mouthful are more than 600,000 trillion water molecules. Each water molecule has 3 atoms, so you're already near 2 times 10 to the 24th atoms from one sip. A glass of water? You're comfortably in the 10 to the 25th power range. That's more atoms in one glass than there are stars in the observable universe. Grab a sugar cube, about 4 grams. Depending on the exact sugar, you're again talking on the order of 10 to the power of 22 to 10 to the power of 23 molecules, each made of dozens of atoms. Even a tiny grain of salt you can barely pick up has billions of atoms in it, all sitting in a neat crystal lattice. Now scale up to you. A 70-kilogram human is mostly water, carbon compounds, proteins, fats, salts, all built from lightweight elements like hydrogen, oxygen, carbon, nitrogen. Run the numbers and you get around 7 times 10 to the 27th atoms. That's a 7 with 27 zeros. All of them in motion, all of them obeying the same quantum rules, all of them in a structure stable enough for you to watch a video and fall asleep. Even air, the stuff you don't see, is full of astronomical counts. One breath is on the order of 10 to the 22nd power molecules. You breathe in and out more individual particles in a few seconds than there are grains of sand on all of Earth's beaches. That's what the atomic scale does. It makes everything a crowd. A trace amount of something in air can still mean millions of molecules per cubic centimeter. A small dose of a medicine can still mean billions of active molecules circulating in your blood. A thin layer of metal on a chip is still hundreds of thousands of atoms thick over an area that contains trillions of atoms. This is why chemistry works so well at our size. Even a tiny reaction, even a weak acid, even a mild smell involves armies of atoms acting together. And because there are so many, their average behavior is smooth. That's the punchline. The world looks continuous because the building block is so small that you always have enough of them to hide the grain. Walls look flat, not because there aren't bumps, but because the bumps are a few hundred atoms high on a surface with billions of atoms across. Liquids look uniform, not because molecules aren't jostling, but because there are so many in every drop that you never see gaps. You are never dealing with one atom in daily life. You are always dealing with numbers so large that only statistics describes them. So when we say the actual scale of atoms compared to everyday things, this is the other half. Not just that atoms are 10 billionths of a meter, but that even the smallest everyday thing you touch is made from crowds of atoms so huge that your brain, your eyes, and your fingers can only see the averaged out result. By now you might be thinking, all right, atoms are unbelievably small, the nucleus is even smaller, and everything is charged. So why doesn't the whole atom just suck itself inward and become a tiny dot? If the nucleus is positive and electrons are negative, shouldn't the electrons just fall into the nucleus and make the atom even smaller than 10 to the negative 10th meters? That's a good instinct, and it's exactly where classical physics runs out of steam. At the atomic scale, the rules change, and the rule that matters most here is that electrons don't behave like little planets orbiting the sun. They behave like waves that can only sit in certain allowed patterns around the nucleus. Think of a guitar string. You can have certain notes on it because the wave has to fit along the string. You can't get every possible shape, you get the shapes the string allows. Electrons around a nucleus are like that. They can only exist in specific energy levels, shells, where their wave-like nature fits the electric pull of the nucleus. The lowest of those levels is the ground state. An electron in the ground state has nowhere lower to fall. If it tried to get closer, its position would become more certain, and quantum mechanics says that makes its momentum more uncertain. In practice, it would start zipping around so energetically that it would push itself back out. There is a balance point where the electron is as close as it can be without violating these quantum rules. That balance point is what gives the atom its size. That's why hydrogen atoms all over the universe are the same size. That lowest energy state is a fixed solution to the equations. On top of that, no two electrons in the same atom can share the exact same quantum state. This is the Pauli exclusion principle. So you can't just pile electrons on top of each other at the nucleus, even if you wanted to. They're forced to spread out into different shells and orbitals, which gives bigger atoms, bigger electron clouds. So atoms don't collapse because the universe won't let them take up less space than the quantum rules allow. Now connect that to everyday stuff. The reason wood has a certain density, water has a certain density, metals have a certain density is because atoms cannot be packed arbitrarily tight. Their electrons set a minimum spacing. Heat something and the atoms vibrate harder, pushing against that spacing, so the material expands. Cool it and the vibrations slow, so it contracts, but only down to the spacing the electrons allow. Try to squeeze a solid and you feel resistance because you're trying to force electron clouds closer than their happy quantum distance. That's why your hand stops at the table, why air can be compressed only so far, why the Earth's interior is so hard to crush. Billions upon billions of atoms all sitting at their minimum allowed distances. If atoms were just little charged marbles without quantum rules, matter could collapse to almost nothing, and your desk could weigh 1,000 tons. Instead, quantum mechanics holds everything open. And this is the part that ties back to the title. The actual scale of atoms compared to everyday things is not a random size. It is a size enforced by the laws of the very small. Atoms are about 10 to the negative 10th meters, not because nature got lazy, but because that's where electrical attraction and quantum uncertainty call a truce. Everything you touch, paper, hair, glass, metal, your own bones, is built on top of that truce. So far we've been talking about an atom like it's one standard little 10 to the minus 10 meter bubble. But real matter isn't built from just one size. Hydrogen, carbon, oxygen, iron, they all sit in roughly the same neighborhood of small, but they are not clones. And that variation in atomic size is exactly what lets everyday materials behave so differently. Let's unpack that in plain English. At the center of every atom is a nucleus with some number of protons. That number is the element's ID card. 1 proton, hydrogen, 6 protons, carbon, 8, oxygen, 26, iron. Around that nucleus sit electrons, and the positive nucleus is pulling on those negative electrons. The stronger the positive charge, more protons, the harder it pulls. But electrons can't all sit right at the nucleus. Remember Act 6, they have to occupy allowed energy levels, the shells. The first shell is close and can only hold 2 electrons. The second shell is farther out and can hold 8. The third shell is farther still and can hold even more. So as you go down the periodic table, you're doing 2 things at once. You're adding protons to the nucleus, which pull inward, and you're also adding electrons, which have to spread out into higher shells, which push the edge of the atom outward. Those 2 effects fight. Across a row of the periodic table, say from sodium to argon, you're adding more protons but not starting a brand new shell. That stronger positive charge pulls the existing electrons in tighter, so atoms can actually get smaller as you go to the right. Then when you drop down to the next row, you start a new shell farther from the nucleus, and the atom suddenly gets bigger again. That's why we don't have one atomic radius, we have a map of radii. And that map explains a lot of everyday stuff. Sodium atoms are relatively big and only have 1 electron in their outer shell. They don't hold it very tightly, so sodium likes to give that electron away. That's why table salt forms so easily with chlorine. Chlorine, in the same row, has more protons and pulls its electrons closer, so it's a bit smaller and very eager to take on 1 more electron to complete its shell. Metals in general have outer electrons that sit relatively far from the nucleus compared with the pull. Those electrons can move, which is why metals conduct electricity. Noble gases have full outer shells at nice stable radii. They don't want to gain or lose electrons, so they don't react much. Even water's weirdness, why it's liquid when similar small molecules are gases, has to do with how oxygen's electron cloud is shaped and how close hydrogen can get before those clouds push back. All atomic scale decisions, all dictated by size and charge. Now compare that to everyday things like plastic, glass, and steel. Plastics are built from big chains of carbon atoms with hydrogen and maybe oxygen attached. Carbon is small enough and flexible enough in how it bonds that you can make long, tangled molecules. Glass is mostly silicon and oxygen in a network. Silicon is bigger than carbon, and the way oxygen bonds to it makes a rigid, non-crystalline structure. Steel? That's iron atoms, pretty large as atoms go, in a metallic lattice with carbon atoms, smaller, squeezed into the gaps. And that mix changes hardness. None of that works if all atoms were the exact same size, or if they could all sit at the same distance from one another. The slight differences in atomic radii, all in that 10 to the minus 10 meters zone, decide what can pack with what, how tightly, in what pattern, and with what strength. And remember our earlier comparisons. A human hair is about 700,000 atoms across. That means a change of even one atomic layer, one extra 10 to the minus 10th meter, is nothing to your eye but everything to chemistry. At our scale, adding 1 millimeter to a wall is meaningless. At the atomic scale, adding 0.1 nanometer to the distance between atoms can turn a good electrical conductor into a poor one, or change how light reflects, which is exactly how some coatings and nanomaterials work. So when we say the actual scale of atoms compared to everyday things, part of that truth is that everyday things owe their look, feel, strength, and even color to differences measured in fractions of a nanometer. Your countertop, your phone screen, the paint on your car, all of them are just what happens when slightly different sized atoms find the arrangement that costs them the least energy. That's the level of precision your whole world is built on. We've said two things that sound like they should cancel each other out. 1, atoms are mostly empty space, and 2, everyday objects are solid. On the surface, that sounds wrong. If you build something from emptiness, shouldn't you get more emptiness? But this is where the atomic scale does its best trick. Solids don't come from one atom. Solids come from astronomical numbers of atoms, all arranged so that their do not enter zones overlap. Picture one atom again as that stadium with the P nucleus in the middle and the fuzzy electron cloud at the edge. One stadium by itself is fragile. You could imagine something slipping through between the seats. But now, imagine millions of stadiums, all packed together, all with their outer rows pushed up against each other. If you tried to walk through that city of stadiums, you'd hit a wall of seating almost immediately. That's what matter is doing. Every atom's electron cloud says no closer than this. And when you stack atoms in a crystal, or in a dense liquid, or even in your skin, those no-go zones form a continuous barrier. This is why the surface of a table feels uniform, even though the atoms at the top are individual. At room temperature, those surface atoms are vibrating, but only by tiny fractions of their spacing. They never move enough to open big gaps. Your finger, made of the same kind of vibrating atoms, comes down, the electron clouds meet, the repulsion spikes, and your nerves report solid. You never get anywhere near the nuclei because the electron-electron repulsion ramps up long before that. And remember the counts from earlier. A sheet of paper is about 1 million atoms thick. A human hair is about 700,000 atoms across. A fingerprint ridge is roughly 1 million atoms tall. So even if one or two atomic layers have slight gaps or defects, and they do, there are hundreds of thousands of layers underneath them backing them up. At our scale, your finger averages over all of it and just feels flat. This crowd effect is also why materials have different hardness. In a metal, the atoms are in a lattice, but the outer electrons are shared, so layers of atoms can slide over each other. That's why metals can be bent. In diamond, the carbon atoms are locked in a very rigid three-dimensional network, so their nope zones are tied together more tightly. That's why diamond is so hard. Same basic atoms, same 10 to the minus 10 meters spacing, just arranged differently, so the crowd of repelling electron clouds either lets layers move or refuses. Even liquids, which don't have fixed positions, are still crowded enough that you can't run through them. Try punching water and you'll see the resistance. The atoms and molecules in water are jostling and moving, but there are still plenty of them per cubic millimeter that your hand can't ignore the forces. Gases are where the crowd thins. The atoms or molecules are far apart, so you can stick your hand through air. But even there, every collision is still electron cloud meeting electron cloud. You never actually touch the air molecules, you bump into their force fields. So the real picture to sleep on is this. You live in a universe where everything large is made from things small, everything solid is made from things mostly empty, and everything reliable is made from things that individually would let you through, but together refuse. Solidity is an emergent property. It appears only when you have enough atoms packed close enough that their quantum and electric rules overlap into a wall. That's the actual scale of atoms compared to everyday things. Your desk, your door, your pillow. They work not because atoms are dense marbles, but because atoms are so small you can fit untold numbers of them into every millimeter. And when you do, their invisible boundaries merge into something your hand can't ignore. By now you might be wondering, if atoms are 10 billionths of a meter across, and if they're mostly empty space, how do we know any of this is real and not just a nice story? We can't point a normal camera at an atom. We can't take a selfie with a carbon nucleus. Visible light, the stuff our eyes use, has wavelengths around 400 to 700 nanometers. That's hundreds of times bigger than an atom. Trying to see an atom with visible light is like trying to pick up a grain of sand with oven mitts on. The tool is too big. So scientists got sneaky. Instead of looking directly, we watched how atoms affect things that we can measure. The classic example is Rutherford's gold foil experiment. A beam of alpha particles was shot at an ultra-thin sheet of gold. If atoms were solid blobs, those particles would bounce a lot. If atoms were smeared out pudding, they'd pass through gently. What actually happened is that almost all the particles passed straight through, telling us most of the atom is empty, but a tiny fraction bounced back hard, telling us there's a tiny, dense, positively charged core. That's how we got the nucleus. Then came X-ray crystallography. X-rays have much shorter wavelengths than visible light, small enough to interact with the spacing between atoms in a crystal. When you fire X-rays through an ordered solid, they scatter in specific patterns, like ripples overlapping on a pond. From those patterns, you can work backward and figure out how far apart the atoms must be. Over and over, the math said about 10 to the negative 10th meters. Electron microscopes pushed it further. Electrons can behave like waves too, and their effective wavelengths can be made incredibly small by speeding them up. If you focus a beam of electrons onto a sample and watch how they scatter, you can build images with way more detail than any optical microscope. That's how we got pictures of viruses, tiny machine parts, even individual layers of atoms in materials. And then, in the 1980s, we built tools that don't use light at all. scanning tunneling microscopes, STM, and atomic force microscopes, AFM. An STM works by bringing an absurdly sharp tip, only a few atoms wide, extremely close to a surface. So close that electrons can tunnel between the tip and the surface because of quantum weirdness. That tunneling current depends on how far the tip is from the atoms underneath. Move the tip across the surface and measure that current, and you can map the bumps, the atoms, one by one. Those iconic images of rows of little humps that say, "This is what atoms look like on copper." That's STM data turned into a picture. A FM is similar, but measures tiny forces instead of tunneling current. None of these are photographs in the everyday sense. They're reconstructions from how atoms push, pull, or scatter things. But the key point is this. Every one of those totally different methods keeps giving the same story. Atoms are real. They sit at separations of about 10 to the minus 10 meters. They have dense centers, and their surfaces can be mapped. That's why scientists talk so calmly about something you've never seen. We've poked the tiny world from 10 different directions, and it always pokes back the same way. And this ties right back to our theme of compared to everyday things. The reason you can't see atoms is not because they're mystical, it's because your eyes use the wrong size of light. It's like trying to read small print with a giant flashlight, too blunt. So we built smaller flashlights and new tricks. The everyday world didn't shrink. We just learned to reach down to where it starts. So far, we've treated atoms like neatly parked cars in a huge lot. Fixed distances, tidy layers, everything in place. That's good for understanding size, but it hides another truth. At the atomic scale, nothing is truly still. Temperature, the thing your weather app tells you about, is just a measure of how much atoms and molecules are moving and jiggling, even in a solid table, where atoms are locked into a crystal or a tangled network. Each atom is vibrating around its spot. Not centimeters, not even micrometers, tiny rapid shivers around its equilibrium position. The hotter the material, the bigger and faster those shivers. That's why things expand when heated. The atoms are pushing a little harder against their neighbors' electron clouds, so the average spacing increases. Cool something down, and the opposite happens. The vibrations get smaller, the atoms settle in a little closer, and the solid contracts. At our scale, this looks smooth. A metal rod gets slightly longer when heated, ice shrinks when cooled. At the atomic scale, it's just trillions of tiny oscillations changing amplitude. In liquids, the motion is even more obvious. Atoms and molecules in water aren't fixed. They're sliding past each other, forming and breaking weak bonds, bumping into their neighbors non-stop. That sloshing at the atomic level is why liquids can flow. In gases, atoms are far apart and flying freely, slamming into each other and into the walls of the container. The pressure of a gas is just all those atomic collisions hitting the walls. You can't see it because atoms are too small, but the behavior of a balloon or a bicycle tire is literally just atomic scale billiards. Now connect that to everyday things. When you smell coffee across the room, what's really happening is that coffee molecules, built from atoms, have enough thermal energy to break away from the liquid, bounce through the air, and eventually collide with the receptors in your nose. When sugar dissolves in tea, water molecules jostle sugar molecules apart and carry them away, making the mixture uniform. When metal feels cold to the touch, it's because the atoms in the metal are very good at passing along vibrations. They pull energy out of your skin's atoms quickly, so you feel the drop. All of this motion is happening at the 10 to the minus 10 meter scale, everywhere, all the time. Even you, lying still listening to this, are a storm. The atoms in your skin are vibrating. The water in your cells is sloshing. Oxygen molecules are ricocheting through your lungs. enzymes are grabbing and releasing molecules in your blood, all through atomic scale collisions. Your body temperature, 37 degrees Celsius, is just the level of motion your atoms are currently enjoying. And it's worth remembering, none of this motion makes you look blurry because there are so many atoms that their individual jitters average out. A wall doesn't melt just because the atoms are vibrating. There are enough of them in a strong enough arrangement to hold shape. That's the constant theme of this topic. Atoms are incredibly small, so you always have so many of them that their messy, jittery behavior turns into smooth, reliable, everyday physics. The true scale of atoms isn't just they're small, it's they're so small that even chaotic motion looks calm when you stack trillions of them into a tabletop. Now that we've dragged atoms out of the abstract and made them stand next to paper, hair, dust, and even your breath, we can talk about the real payoff of being that small. You can build unbelievably detailed things in unbelievably small spaces. If atoms were, say, a millimeter across, you could not have cells the size of cells, or proteins that fold, or DNA spiraling inside a nucleus. Everything would be blocky and coarse, like trying to paint a portrait with fist-sized brushes. But atoms sit down at 10 to the minus 10 meters, so nature can use them like pixels. Not the big pixels on an old TV, but microscopic pixels you can stack, twist, and join in trillions. Think about DNA. One human cell has about 2 meters of DNA packed inside it if you stretched it out. 2 meters, taller than you. Yet it's coiled, looped, and folded so efficiently that it fits inside a nucleus maybe 10 micrometers across. How is that possible? Because DNA is built from molecules, and molecules are built from atoms, and atoms are so small you can make long chains and still keep the whole structure in tiny real estate. Proteins are the same. A protein might have hundreds or thousands of atoms arranged in a very exact three-dimensional shape. That shape determines what it does. Maybe it carries oxygen, maybe it digests sugar, maybe it sends signals between cells. Change one atom in the right spot and the whole protein can behave differently. At our scale, swapping one brick in a building does nothing. At atomic scale, swapping one atom in a molecule can turn something helpful into something toxic, or make a plastic more flexible, or make a semiconductor conduct more efficiently. That's how sensitive the world is down there. Even non-living materials show this. Carbon, arranged one way, gives you soft graphite. Layers of carbon atoms that slide over each other, like in a pencil. Carbon, arranged another way, gives you diamond. Every atom bonded strongly in a rigid 3D network. Same element, same sized atoms, different pattern, completely different everyday thing. Silicon, the backbone of modern electronics, works because at the atomic scale you can slip in other atoms, dopants, to change how easily electrons move. You don't have to add whole chunks. A few atoms per million is enough to change the behavior. That only makes sense when your base unit is so small that even a tiny fraction still means lots of actual atoms. And now tie that back to the title of the video. The actual scale of atoms, compared to everyday things, isn't just a flex about how small atoms are. It's the reason everyday things can be this intricate. Your eye, your ear, your nervous system, the pigments in leaves, the hardness of rock, the viscosity of honey. All of them rely on being able to arrange matter at submicroscopic resolution. Atoms give you that resolution. 100,000 atoms take up about the width of a dust speck. 1 million atoms take up the thickness of paper. 1 billion atoms can fit in volumes so small you can't see them. That's why a cell, which is already too small for you to see, can still contain organelles, membranes, channels, pumps, and even viruses inside it. Everything fits because the building block is tiny. And because the building block is tiny, you can get emergent properties. Things that don't make sense if you look at just one atom. One water molecule is nothing special. Trillions of water molecules together get surface tension, can dissolve salt, can flow, can form waves. One atom of iron won't stick to a magnet. Trillions of iron atoms lined up in domains will. One pigment molecule isn't a color. Lots of pigment molecules absorbing the same wavelengths give you blue paint. Complexity, color, life. They're all just what happens when the universe uses a unit so small that it can repeat it nearly endlessly inside objects you can hold. That's the quiet genius of the atomic scale. It hides the grain so you can live in a smooth world. So far, we've been looking at atoms in space, their size, their spacing, how many of them fit in paper or hair. But there's another gap between the atomic world and our world, and that's time. At the atomic scale, things happen fast. Collisions between gas molecules happen in billionths of a second. Vibrations of atoms in a solid happen trillions of times per second. Electrons jumping between energy levels, bonds forming and breaking, molecules rotating. All of it runs on a clock far, far quicker than anything we perceive. You don't see any of it because your brain runs on a much slower loop. Your eyes and nerves need milliseconds to notice something. Atoms are done with their business before your cells even know something happened. So what you experience, what you call "this table is solid" or "this water is warm," is the average of countless atomic events happening underneath. Take temperature again. When we say something is 20 degrees Celsius or 37 degrees Celsius, what we mean is that the atoms or molecules in it have, on average, a certain amount of kinetic energy. They're moving and vibrating at a certain intensity. But at any moment, individual atoms are moving faster or slower, bumping into neighbors, swapping energy. None of those individual bumps are reported to you. Your senses get the big picture. It's warm. Same with smell. One coffee molecule reaches your nose. Nothing. Millions of them over a short time. I smell coffee. At the atomic scale, diffusion, the random wandering of molecules, is chaotic and jittery. At our scale, it looks smooth, a smell spreading across the room. Even dissolving sugar is like this. At the atomic level, water molecules hammer sugar molecules off the crystal one at a time, wrap them, and carry them away. You can't see those micro-kidnappings. You just see the sugar cube getting smaller until it's gone. The world looks continuous because we are too slow and too big to see the grainy, jumpy steps. This matters for our topic because it answers a nagging question. If atoms are spaced out and zipping around, why doesn't everything fall apart? The answer is number and speed. There are so many atoms in even a tiny volume that any local wobble is cancelled by neighbors, and any gap is filled almost instantly. Think about air. A cubic centimetre of air, a sugar cube volume, has about 10 to the power of 19 molecules in it. Even if a bunch of them fly out of that spot, others fly in. So air looks uniform, water is even tighter. In a liquid, any small vacancy is filled right away because surrounding molecules are moving and colliding all the time. That's why you don't see blinking holes in your glass. Solids are the slowest, but even there, atoms are vibrating so quickly that to your eyes the surface is a steady plane. It's a bit like watching cars on a highway from far away. Up close, each car is speeding up, slowing down, changing lanes. From a hill, the highway looks like a smooth flow in one direction. Atoms are the cars. Your senses are on the hill. And this is exactly why we needed special instruments to see atoms in Act 9. We had to slow down and magnify motion that is too fast and too small for us. So when we say the actual scale of atoms compared to everyday things, we should also whisper, and the actual speed of atoms compared to everyday time. Your coffee cup, your desk, even your own body is being constantly rebuilt, jostled, rearranged at an atomic level, but the numbers are so enormous and the steps so quick that you only ever meet the averaged out object. That's good news. It means you can go to sleep while the universe keeps quietly updating you at 10 to the 27th atoms. So far, we've talked about atoms as little units of matter, but atoms also decide what you actually see in the world, the colors of things, the way metals shine, the way glass is transparent. And again, it all comes down to their scale. Light is an electromagnetic wave, and different colors have different wavelengths. Red is longer, blue is shorter, ultraviolet is shorter still. When light hits an object, what happens to that light depends on whether the electrons in the atoms of that object can jump between energy levels that match the light's energy. Remember from earlier, electrons in atoms can't sit anywhere they want. They can only sit in specific energy states. Going from one state to a higher one takes a specific amount of energy. If a photon of light arrives carrying exactly that amount, the electron can absorb it and jump up. If the energy doesn't match, the atom ignores it. That's why some things have color. A leaf looks green because the molecules in it, chlorophyll, have electrons that happily absorb red and blue light, but not green. Green light gets reflected or transmitted, so that's the color that reaches your eyes. All of that selection is happening at the atomic and molecular scale, at distances of nanometers, with electrons jumping over energy gaps set by how atoms are arranged. Metals are shiny for a related reason. In metals, some electrons aren't tied to one atom, they're free to move through the lattice. When light hits, those electrons can slosh in response, reflecting a lot of the incoming light. Again, that's a property set by how atoms are spaced and how their electrons are allowed to behave. Glass and clear plastic are transparent to visible light because their electrons don't have energy jumps that match visible photons. The light goes through. But the same material might block ultraviolet because those photons have enough energy to excite the electrons. So your sunglasses work not because someone painted UV off onto them, but because the atoms in the lenses are arranged in a way that rejects certain photon energies. Even black paint is just a material full of atomic and molecular structures that can absorb a broad range of photon energies and convert them into vibrations, heat. The paint looks black because it doesn't send much light back. That's all atomic/molecular scale work. Now connect this back to everyday things. A red shirt under white light looks red because hundreds of trillions of photons per second are hitting it, and only the red ones are bouncing back to your eyes. Every photon that doesn't match an allowed energy transition gets eaten. Those allowed transitions? They're set by electron arrangements. Electron arrangements? Set by atomic spacing and which atoms are bonded to which. Atomic spacing? Right back down to that 10 to the minus 10 meter zone. Even more dramatic, why do thin films, like oil on water or anti-reflective coatings on glasses, make rainbow colors? Because the thickness of the film is on the order of the wavelength of visible light. Some colors interfere and cancel, others reinforce. You can only get that effect because we can make layers that are a few hundred nanometers thick, a few thousand atoms stacked, and light is sensitive to differences that small. The real practical world uses this all the time. Screens, camera sensors, solar panels, LEDs, all of them rely on arranging matter at or near atomic scales so that electrons will do exactly what we want when light hits. You get to see YouTube videos because silicon atoms in your device are arranged in such a way that moving charges around produces a controlled image. So when we compare atoms to everyday things, we shouldn't just think in terms of this many atoms fit across a hair. We should also think the way this hair looks, the way this screen glows, the way this glass lets light through. All of that is decided by atoms, sitting in their 10 to the minus 10 meter positions. The colors of the macroscopic world are whispers of the atomic world. Up to now, we've mostly talked about atoms as if they were lined up politely, like in a diagram. Real life is messier. The air you breathe, the water you drink, and the rock under your feet are all made of atoms at the same basic 10 to the minus 10 meter scale, but they behave completely differently because of how tightly those atoms are packed and how strongly they grab each other. Let's start with air, because it's the easiest to picture once you shrink yourself down. Air at room temperature and pressure is mostly nitrogen and oxygen molecules zipping around in a big empty hall. Each molecule is only a few atoms big. Nitrogen is 2 nitrogen atoms, oxygen is 2 oxygen atoms, and the distance between neighboring molecules is much bigger than the molecules themselves. They move fast, collide, bounce off, and go flying again. That's why you can wave your hand through air. The atoms and molecules are far apart enough that your hand can shove them out of the way. But don't let the emptiness fool you. A sugar cube volume of air, just 1 cubic centimeter, still contains around 10 to the power of 19 molecules. That's 10 billion billion. If you could see at their scale, the room you're in right now would look like an insanely crowded 3D highway of particles, all moving at hundreds of meters per second, slamming into you, the walls, and each other. It only looks empty because the particles are too small to see, and because your eyes average over huge numbers of them. Now drop into water. Water molecules are also tiny, about 0.3 nanometers across. But in liquid water, they are much closer together than air molecules. They're constantly moving, but they're also constantly forming and breaking weak hydrogen bonds with their neighbors. So instead of a huge empty hall, liquid water is more like a crowded dance floor where everyone is bumping, linking hands, letting go, and grabbing someone else, all in trillionths of a second. That's why water is hard to compress. The molecules are already close. Try to force them closer, and their electron clouds start repelling strongly. But it can still flow because those bonds are temporary. Atoms at the same 10 to the power of minus 10 meters scale, just packed and linked differently. Now go even tighter. Rock, metal, bone, solids. Here, atoms are locked into fixed positions in a lattice or a tangled network. The distance between neighboring atoms is still in that 0.1 to 0.3 nanometer range, but now the atoms can't just wander away. Bonds are strong, positions are fixed, motion is reduced to vibration. That's why rock holds shape. That's why metal beams stay straight. That's why your desk doesn't sag like water. And yet, even here, the scale is the same. 10 to the minus 10 meters between atomic centers, 1 million atoms thick for paper, hundreds of thousands across for a hair. It's just that in solids, every atom's do not enter zone is pressed right up against the next ones, making a continuous barrier. What's wild is that you can move between these states just by changing energy or pressure. Heat water enough and it becomes steam. The molecules get enough energy to escape their neighbors and act more like air. Cool steam and the molecules slow down, come closer, and water appears. Freeze water and the molecules settle into a solid lattice, ice, where they're more fixed. Same atoms, same scale, same oxygen and hydrogen, totally different everyday behavior. The atomic scale stays the same, the arrangement changes. And here's the part that ties it back to compared to everyday things. All the objects in your room, air, water in a glass, plastic on your mouse, paint on the wall, are made from atoms that are basically the same size, all sitting somewhere around 1/10 of a nanometer apart. Your eyes report them as completely different kinds of stuff because of how those atoms are arranged and how tightly they hold each other. Air feels like nothing because the atoms are spread out. Water feels fluid because the atoms are close but not locked. Solids feel solid because the atoms are close and locked. The scale underneath never changed. That's the real lesson. Once you understand the atomic scale, you don't have to memorize that water is a liquid and rock is a solid. You can see that if you take the same 10 to the negative 10th meters dots and either space them, slide them, or lock them, you get all the everyday materials you know. Touch feels so basic. You put your hand on the table and your nerves say table. You hold a glass and your fingers say smooth. It would be natural to think that the atoms in your skin are pressing right up against the atoms in the table or the atoms in the glass. But that's not what's happening. At the atomic level, touch is not atoms colliding like billiard balls. It's atoms getting close enough that their electric fields start pushing back hard. Remember from earlier acts, every atom is a tiny positive nucleus surrounded by a cloud of negative electrons. Those electrons don't like getting too close to other electrons. When two atoms approach, the outer parts of their electron clouds overlap, and because like charges repel, the energy of the system shoots up. That repulsion rises so quickly that it behaves like a solid barrier. Your hand stops, not because atoms have literally hit other atoms, but because the force got too big to push through. It's like trying to push two strong magnets together, north to north. They never actually touch, but the resistance is so real, your muscles feel it. Now scale that up to whole objects. Your hand is made of billions upon billions of atoms. The table is made of billions upon billions of atoms. And when you bring them together, the outer electrons of both objects create a shared, no-father zone. Your skin receptors are pressure sensors. They detect how much force is being redirected back into your hand. That force is just electrons being grumpy about sharing space. So at a fundamental level, you have never actually touched anything in your life. You have only ever gotten close enough for electrons to strongly disagree. This also explains why different materials feel different, even though it's all electrons all the way down. A soft material, like a cushion or your skin, has atoms and molecules arranged in a way that allows a bit of movement. Chains can slide, gaps can compress. So when your hand pushes, the electrons don't all resist at once. The force builds slowly, and your brain calls that soft. A hard material, like metal or glass, has atoms locked into a stiff arrangement. Push on it, and many atoms push back together, so the force ramps up quickly. That's hard. But in both cases, the maximum approach distance is still set by the same atomic scale rule. Electron clouds won't let you in. Even adhesion, things sticking together, fits this frame. When two very clean flat surfaces are put together, the atoms on each surface can get close enough for weak attractions, like van der Waals forces, to show up. That makes the surfaces stick, even without glue. At that moment, the outer electrons of one object are interacting directly with the outer electrons of the other. But they're still not merged. They're just close enough that attractive forces balance repulsive forces. Your phone screen, your fingerprints on glass, dust landing on a shelf. All of this is atoms negotiating how close they can stand each other. And this is the bit people forget when they hear atoms are mostly empty. Yes, they're mostly empty on the inside, but the edges are loud. The forces at the edges are strong enough and act over short enough distances that from our scale it might as well be a brick wall. That's why a mosquito can land on water. The water's surface atoms hold together and resist. That's why geckos can walk on walls. The microscopic hairs on their feet get close enough to surfaces for those weak atomic attractions to add up. That's why your bed feels supportive, even though it's made from empty atoms. Millions of atomic force fields overlapping make a macroscopic force. So when you rest your hand on something tonight, remember what's actually happening. Two vast crowds of atoms are standing near each other, their electrons pushing and pulling, and the message your nerves send to your brain is simply, we have reached the boundary. Now that we know atoms are all living down around the 10 to the minus 10 meter mark, a new question shows up. If everything is made from atoms that are basically the same size, why do some things feel light and others feel heavy? Why does a block of wood the size of your fist feel fine to hold, but a block of lead the same size feels like it's trying to escape your hand? At the atomic scale, that difference mostly comes down to how much mass you can cram into a certain volume of space. In other words, density. And density is just atoms and nuclei doing math. Let's break it down in plain English. An atom of hydrogen is tiny and has just one proton in its nucleus. An atom of oxygen is about the same overall size as hydrogen. Electrons set the size. But it has 8 protons and usually 8 neutrons in the nucleus. So the space taken up by a hydrogen atom and an oxygen atom isn't wildly different, but the stuff inside the oxygen nucleus is much, much more. Jump to iron, 26 protons, about 30 neutrons. Lead, 82 protons, around 125 neutrons. You can see the pattern. The electron cloud, the thing that sets how far apart atoms sit, doesn't grow nearly as fast as the mass in the nucleus does. So you can have two materials where the atoms are spaced at roughly similar distances, still in that 0.2 to 0.3 nanometer separation, but one of those materials has atoms whose nuclei are way heavier. Pack a room with beach balls and pack the same room with bowling balls. Same volume, totally different weight. That's what's happening in your hand with wood versus lead. Wood is made mostly of light elements, carbon, hydrogen, oxygen, some nitrogen. Lead is made of lead. Its atoms are just heavier per atom slot. That's why a small piece feels heavy. Now add in how tightly atoms can pack. In some materials, atoms line up in very efficient arrangements. Crystals where every atom has neighbors in fixed positions, not much empty space between the electron clouds. Metals are good at this. In other materials, like wood, there's structure made from long molecules with gaps, pores, and even air in between. At the atomic scale, those gaps are just regions where you could have fit more atoms but didn't. So a cubic centimeter of wood contains fewer atoms than a cubic centimeter of copper, and the atoms in copper are heavier. Double whammy. Fewer and lighter versus more and heavier. That's density. You experience it as heaviness, but it's just counting nuclei per volume. Here's where it ties back to our main theme. Even when you pick up something heavy, like a dumbbell, the atoms in it are not closer than atoms in your arm by some huge amount. We're still talking on the order of tenths of nanometers between atomic centers. We're still talking electron clouds stopping atoms from getting too close. We're still talking millions of layers in a millimeter. The heavy object just has more massive nuclei tucked into that same atomic spacing. Same size boxes, heavier contents. This is also why water is weird and cool. Liquid water packs its molecules fairly tightly. That's why it's hard to compress. Ice, however, locks those molecules into a crystal that actually has more open space, so ice is less dense and floats. At the atomic level, that just means, in ice, the water molecules are held in positions that don't maximize how many you can fit in a given volume. Same atoms, same 10 to the minus 10 meters scale, but a slightly less efficient packing pattern gives you a chunk that rides on top of its own liquid. Everyday life is full of these atomic packing stories. Aluminum feels light for its size because aluminum atoms are relatively light and arranged in a metal lattice that isn't the densest possible. Gold feels heavy because gold atoms are much heavier, and the atoms are still sitting right up against each other. Plastic feels light because it's made of long chain molecules with plenty of empty space between them at the microscopic level. Stone feels solid and heavy because silica-based minerals can pack tightly and are made from elements that aren't featherweight. You can even see density and color sometimes. Metals with tightly packed electrons reflect light in particular ways, while low-density foams scatter it. But underneath all of it is the same thing we've been saying since Act 1, the actual scale of atoms doesn't change. Everything you touch, feather, rock, phone, water bottle, is built from units about 1/10 of a nanometer wide. The difference is how much mass is inside each unit and how efficiently you can arrange those units without violating electrons' no-closer rule. So the next time you pick up something and think, this is heavy, know what your hand is really reporting. This object has a lot of closely packed electron bubbles, and inside each bubble, the nucleus is stuffed with protons and neutrons. Heaviness is just the macroscopic way of noticing that, atom for atom, this thing is carrying more in the same tiny space. When we talk about objects, we usually think of them as big, solid chunks. This is glass, this is metal, this is skin. But the part that actually talks to the outside world is only the very top skin of atoms, and in atomic terms, that top is laughably thin. The surface of your phone screen, your table, a raindrop, or even your own fingertip is only a few atomic layers thick, maybe a few dozen to a few thousand atoms, and yet that is the layer that decides whether something looks shiny or dull, whether water beads up or spreads out, whether fingerprints stick or wipe away. Everything beneath that thin film can be perfectly normal glass or metal, but you will never meet it, because your eyes, light, air, and oils only ever interact with those outermost atoms that have one side exposed. Atoms deeper in the material are satisfied, bonded on all sides, locked into place. But surface atoms are unsatisfied on one side, so they are more reactive and more available, which is why gases stick there, why rust starts there, why coatings work there. Think about rust on steel. The whole steel bar might be centimeters thick, millions upon millions of atoms from one side to the other, but oxidation begins in just the top atomic layers, and already the whole thing looks rusty to you because the surface is the only part your eyes can judge. Or take your phone screen. The glass underneath is silicon and oxygen all the way down, but manufacturers add coatings that are only tens of nanometers thick, a few thousand atoms, to make it repel oil or reduce reflections. That's nothing compared to the thickness of the glass, but because it lives at the interface between object and world, it controls the experience. Even smudges work like this. The oil from your finger can be just a few molecules thick, but once it sits on top of glass, the whole panel looks dirty. A human hair is about 700,000 atoms across. Your smudge might be 50 molecules thick, and your brain cares more about the 50 molecules. That's how loud the surface is. High-tech stuff leans on this constantly. Anti-reflective coatings on lenses are made by stacking layers whose thickness is matched to the wavelength of visible light. A couple of hundred nanometers, only a few thousand atoms. And yet that microscopic sandwich tells light to cancel itself, so it looks clear. Non-stick pans, corrosion-resistant metals, hydrophobic fabrics, even the way gecko feet stick to walls, all surface atom business. So when we talk about the actual scale of atoms compared to everyday things, this is a perfect example. An object can be billions of atoms thick, but a change in the outer 5 to 50 nanometers, the outer few thousand atoms, completely changes how you see it and how it behaves, because at our size we don't experience the bulk, we experience the skin. So far we've been looking at atoms as the hidden foundation of everyday objects, but there's a whole branch of modern science and engineering that doesn't just accept the atomic scale, it deliberately works there, one layer or even one atom at a time, to make materials do things they could never do in bulk. This is where words like nanotechnology, thin films, quantum dots, and semiconductors live. And even though those sound futuristic, the basic idea is very simple. If atoms are only about 0.1 nanometers in size, and if stacking just a few thousand of them makes a visible layer, then we can build devices by adding or removing a few thousand atomic layers in exactly the pattern we want. Think about a computer chip. Inside it are transistors, tiny switches that control the flow of electrons. Those switches are made from silicon that has been doped, which just means a tiny number of silicon atoms have been replaced with different atoms like phosphorus or boron. We're talking a few atoms per million. At our scale, adding a few parts per million to something is nothing, like sprinkling a few grains of sand on a beach. At the atomic scale, that's enough to change how easily electrons can move, and that change is what lets the transistor turn on and off. Your phone, your laptop, your whole digital life depends on the fact that we can tweak matter when changing the identity of a tiny fraction of its atoms. Same with LEDs. The color of the light they emit depends on the energy gap between electron levels in the material, and that gap can be tuned by changing the atoms in the crystal or by making the crystal extremely thin, just a few nanometers, so that electrons are confined. Even the fancy word quantum dot is just a tiny chunk of material small enough, a few nanometers across, that its electrons feel the walls and the dot glows a specific color. Shrink the dot, change the color. That's atomic scale engineering. We also do this with coatings: anti-scratch, anti-fog, anti-fingerprint, anti-reflective, super black. All of those come from depositing controlled, nanometer-thick layers of atoms onto a surface. Remember from Act 17 that the surface is what the world meets. That means if you can put down 10 nanometers of the right atoms, you can make glass repel water, or make metal resist corrosion, or make a lens transmit more light. 10 nanometers is 100 atoms. 100 atoms, chosen and placed well, can make a camera better. And in medicine, we go even smaller. Some drug delivery systems use nanoparticles, little shells or blobs, tens of nanometers wide, because cells and proteins are sensitive to that size range. A cell might engulf a 50 nanometer particle, but ignore a 500 nanometer one. That's a difference of only a few hundred atomic layers in diameter, but at the biological scale, it's the difference between works and does nothing. All of this should make you appreciate just how fine the atomic ruler is. At human scale, if you miss a measurement by a millimeter, nobody cares. At atomic scale, if you miss by 1 nanometer, 10 atoms, the device might stop working. That's how narrow the tolerance is. And yet this is also why the world looks so smooth. Because atoms are so small, we can stack them in exquisite detail. And once we scale that up to something you can hold, it feels continuous. So the actual scale of atoms compared to everyday things isn't just a curiosity. It's the entire reason modern tech works. We found a way to grab the bottom layer of reality, move a few thousand atoms around, and the result is a screen, a chip, a sensor, a lens. Tiny units, huge consequences. So far we've talked as if every atom of a given element is identical. Every carbon the same, every oxygen the same, but the universe is a bit messier and a bit more interesting than that. Atoms of the same element always have the same number of protons. That's what makes them that element. But they don't always have the same number of neutrons. When you change the neutron count, you get an isotope. Same element, same electrons, same basic size, but a slightly different mass. Carbon-12, for example, has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 6 neutrons. 7 neutrons. Carbon-14 has 6 protons and 8 neutrons. All of them are carbon. They all sit in the same spot on the periodic table. They all make the same kinds of bonds. They all fit in the same 10 to the minus 10 meter space because the electrons decide the atom's radius. But because the nucleus is heavier or lighter, the atom behaves just a little differently in physical processes. At our scale, that sounds too small to matter. What's a single neutron between friends? But at the atomic scale, and especially in large numbers, those tiny differences become tools. Water, for instance, is made of H2O, 2 hydrogens and 1 oxygen. But some water molecules have deuterium instead of hydrogen, which is hydrogen with an extra neutron. That heavy water behaves almost the same, but not exactly. It freezes at a slightly higher temperature. It moves a bit more slowly in reactions. And in biology, large amounts of it can mess with life because enzymes are tuned to the masses of ordinary hydrogen. We're talking about a change in mass that doesn't change the atom's size at all, and yet life notices. Geologists use this trick all the time. Oxygen has stable isotopes, mainly oxygen-16 and oxygen-18. Water containing the heavier oxygen-18 evaporates and condenses slightly differently than water with oxygen-16. Over long times, ice sheets and oceans end up with measurably different isotope ratios, and those ratios get locked into shells, sediments, even cave formations. Millions of years later, a scientist can drill into that layer and say the ocean was colder here, just by measuring how many heavy versus light oxygen atoms are in the sample. That entire paleoclimate story rests on the fact that atoms, though nearly identical in size, can carry a different mass in their nuclei. Carbon dating is the same vibe. Cosmic rays in the atmosphere create a small amount of carbon-14, which gets mixed into CO2, which plants breathe, which animals eat. As long as something is alive, it keeps swapping carbon with the environment, and the ratio of carbon-14 to carbon-12 stays normal. When it dies, the carbon-14 starts to decay at a known rate. Measure how much is left compared to the non-decaying carbon-12, and you can tell how long ago it died. That's an atomic scale clock, a single extra neutron in some carbon atoms, ticking away over thousands of years, letting us date wood, bone, cloth. Again, same element, same 10 to the minus 10 meters atom, different nucleus payload. Even in medicine, we use this. Radioactive isotopes, atoms with unstable nuclei, can be attached to molecules that the body naturally takes up, and then doctors can trace where they go because the isotope gives off detectable radiation. The chemistry doesn't change much because the electrons see, yep, still this element, but the nucleus is doing extra work. All of this sits perfectly inside our topic because it shows how much precision the atomic scale gives us. You can have 2 atoms that, to your eyes, if you could see them, would look identical in size and shape, both occupying that standard atomic volume, but one of them is a little heavier and a little unstable, and the universe treats it differently. Everyday objects are made from oceans of these atoms, so they average out and look uniform. But zoom in, measure carefully, and you find tiny fingerprints, slightly heavier oxygen here, slightly less carbon-14 there, and from that you can tell the temperature of ancient seas or the age of a mummy. That's the power of working at 10 to the minus 10 meters. Even the smallest, almost invisible differences can be scaled up into stories about planets, climates, and history. We've been comparing atoms to paper, hair, salt, metal, good, sensible objects. But the place atomic scale really shows off is inside your own body, because your body is a perfect example of everyday thing made from non-everyday sizes. Start with a single human cell. A typical cell might be 10 to 30 micrometers across. From earlier, you know 1 micrometer is 1,000 nanometers, and an atom is about 0.1 nanometers. That means one cell is on the order of 100,000 to 300,000 atoms across. And the cell is full, not of random goo, but of structures: a membrane, channels, mitochondria, a nucleus, DNA, enzymes, scaffolding. Every one of those is made from molecules, and every molecule is made from atoms spaced at that same 10 to the minus 10 meter rhythm. Take your cell membrane. It's basically a double layer of molecules, each a few nanometers long. A few nanometers is a few dozen atoms head to tail. That's it. And yet that film, just a couple hundred atoms thick, is what keeps your cell from leaking out into the world. Your DNA? The famous double helix has a diameter of about 2 nanometers, about 20 atoms across, and yet it carries all the instructions for building you. Squash the atom size even more in your mind, 20 atoms side by side, and nature says that's enough space to encode hair color, eye color, immune responses, how tall you'll be. Proteins are the same story. A protein is a long chain of amino acids, each amino acid made from a couple dozen atoms, folded into a very specific 3D shape. That shape is what lets a protein grab oxygen or cut a sugar or send a signal. If you move even a few atoms in that shape, the protein might stop working. At our scale, moving a few bricks in a house does nothing. At atomic scale, moving a few atoms in a protein destroys its job. That's how tight the tolerances are. Even the water inside you is running on atomic logic. Water molecules are small enough, about 0.3 nanometers, that your cells can line them up and pump them through channels like parts on an assembly line. Those channels are proteins with holes exactly the size of a water molecule, not a big ion, not a sugar. We can build filters in the lab that copy that idea, pores only a nanometer or two wide that let some atoms through and block others. Your kidneys do it every second. Your lungs do it, swapping oxygen and carbon dioxide across membranes that are only a handful of molecules thick. And because all of it happens at 10 to the minus 10 to 10 to the minus 9 meters, it can happen fast and in parallel. Billions of reactions per second in a single cell, and you never notice. Even your bones, which feel like the most macro thing ever, are atomic lattices made smarter. Bone is a composite, hard mineral crystals, hydroxyapatite, embedded in a flexible protein matrix, collagen. The mineral part is atoms in a crystal spaced at that same tiny distance. The collagen is atoms in long chains folded and cross-linked. The result is something strong but not brittle. Teeth, nails, skin, blood, all atom-scale engineering scaled up. So when you look in a mirror, you are looking at 10 to the 27th atoms arranged in layers and networks. Most of those atoms no more than a tenth of a nanometer from their neighbors, and yet together they make eyes, lips, muscles, memory. That's the real meaning of actual scale of atoms compared to everyday things. The everyday thing can be you. You look continuous, but you are a cathedral of nanometer parts. By now it probably feels like we can just keep shrinking things forever. Atoms are tiny, we can stack them, we can coat with them, We can even move them with scanning tips. So why don't we make everything smaller and smaller and smaller until computers are the size of dust and whole machines fit in a cell? The answer is that the atomic scale isn't just small, it's also a flaw. There is a point where matter stops behaving like continuous stuff and starts behaving like individual atoms and electrons again. And when you hit that point, the tricks that work at our scale stop working. Think about a wire that carries electricity. At our scale, you can make the wire thinner and it still conducts. Copper atoms pass electrons along in a nice shared cloud. But if you start making that wire only a few atoms wide, electrons don't move in smooth crowds anymore. They start to feel every bump, every impurity, every atom that's out of place. The resistance can jump, heat can build, and the wire becomes unreliable. The same thing happens in computer chips. For decades, engineers shrank transistors, the little on-off switches, by making the channels that electrons travel through narrower. Smaller channels mean more transistors per chip, which means more power. But once those channels got down into just a few dozen nanometers, and then into the single-digit nanometers, the electrons stopped politely staying in their lane. They started to tunnel, to appear on the other side of barriers they weren't supposed to cross. Because at that scale, quantum mechanics lets particles act like waves. That's an atomic scale rule pushing back on our desire to shrink. You can't tell an electron, no, really, stay right here, if the barrier is only a few atoms thick. The electron can say, I see a non-zero chance I can be over there. And sometimes it just is. Light behaves the same way when we make things too thin. A pane of glass a few millimeters thick is just glass. Thin it down to a few hundred nanometers, a few thousand atoms, and suddenly interference patterns show up, colors shift, reflectivity changes. Go thinner, and you can't even call it glass anymore. It behaves like a film, not a window. Even in biology, there are flaws. Cell membranes can only be so thin, a couple of molecules thick, before they stop being good barriers. Proteins can only be so small before they can't fold into stable shapes. DNA can only be packed so tight before the cell can't access it. All of those we can't go any smaller moments are the atomic scale saying, this is the unit I work with. Below this, the rules change. And material scientists run into this constantly. A bulk piece of gold is yellow and conductive. Make gold into nanoparticles a few nanometers across, only a few dozen atoms, and suddenly it can look red or purple because the electrons are confined, and it might melt at a lower temperature. Same element, but once you're close to the atomic size, you get new behavior whether you wanted it or not. That's great when you're designing a sensor. It's annoying when you want a simple, predictable part. Even measuring things hits this wall. At big scales, you can poke objects without changing them much. At atomic scales, the act of measuring can disturb the thing you're measuring because you have to use energy comparable to the energy holding the system together. Fire a high-energy electron to see where an atom is, and you might knock it out of place. Shine light short enough to see the detail, and the light itself carries enough energy to change the system. So there's a built-in fuzziness at the bottom. That's why we describe electrons as clouds and probabilities instead of little dots at exact coordinates. Nature does not give us infinite resolution, and this is exactly why our whole video topic matters. Everyday things only look unlimited and smooth because they sit so far above the floor that they never hit it. A table can be planed thinner, paper can be pressed thinner, wires can be drawn thinner, but eventually you run into the fact that atoms are 10 to the power of minus 10 meters wide. Electrons won't be pinned more tightly than quantum rules allow, and forces only act so far. That's the real, actual scale of atoms, not just how small they are, but the fact that they set the lower bound for what counts as matter behaving like matter. Everything below that is just particles and probability, and everything above that, including you, your room, and your whole planet, is built on top of that lower bound. We've spent all this time zooming down to the bottom, staring at 10 to the minus 10 meter building blocks, watching them buzz around, repel each other, form thin surface layers, and set hard limits on how small we can go. So now we should flip the telescope and look back up. Because the strangest, most useful thing about atoms is not just that they're small. It's that when you have enough of them, the chaos disappears and big smooth rules appear. One atom bouncing around is unpredictable. 10 atoms are slightly better, but still messy. 10 trillion atoms, the number you have in a cup of water, suddenly start obeying simple laws like water boils at around 100 degrees Celsius, and ice floats and pressure goes up when you heat a gas. None of those laws are written into a single atom. A lone water molecule doesn't know what boiling point means. A single nitrogen molecule doesn't know it's supposed to have a pressure. Those are emergent properties, behaviors that show up only when you stack ridiculous numbers of atoms together in the same conditions. And this is exactly why the world feels so reliable to us. You can build a bridge and know the steel will hold. You can cook pasta and know the water will boil. You can trust air will fill any container. Not because atoms are well behaved individually, but because there are so many of them that their jitters average out. The law of large numbers, the statistical smoothing that happens when you have vast counts, is the secret sauce that turns a universe of buzzing emptiness into a stable kitchen table. Take gas pressure. At the atomic level, it's just molecules zooming around and slamming into the walls. Each collision is a tiny random event, but there are so many collisions every second, more than you could ever count, that the average force on the wall becomes steady. Your tire doesn't deflate and reinflate every millisecond. It just sits at a pressure because a billion molecules are taking turns hitting the rubber. Temperature is the same. Atoms in a hot object aren't all moving at the exact same speed. Some are slower, some are like rocket ships. But when you average their energies, you get a number. And that number is what we call temperature. That's why a thermometer works. It doesn't read every atom, it just reads the average motion and reports it like it's a single truth. Even solidity, the thing we keep coming back to, is emergent. One atom can't be solid. Two atoms can pull together or push apart. A crystal made of quadrillions of atoms, each refusing to let their electron clouds overlap too much, becomes a block of salt you can pour or a diamond you can scratch glass with. And it gets even better. The macroscopic physics we teach, Newton's laws, fluid flow, sound waves, all rely on this atomic crowd behavior. Sound, for example, is nothing more than atoms in air bumping their neighbors in sequence. At the atomic level, it's just, I push you, you push him, he pushes the next one. At our level, it turns into a wave we can hear. And because there are so many atoms per cubic centimeter of air, that wave travels predictably enough that we can make music, run jet engines, and talk across a room. If air only had a few atoms in it, sound wouldn't work. So the actual scale of atoms compared to everyday things has a second meaning. Everyday things are only everyday because they are made from so many atoms that the tiny randomness is crushed under averages. You never see a cup of water spontaneously freeze at room temperature, even though, microscopically, you could imagine molecules landing in an ice-like pattern, because statistically, the chance of all of them doing that at once is essentially zero. You never see a solid table suddenly let your hand pass through because, while an individual electron cloud can fluctuate, the odds of billions of atoms all giving way in the same spot at the same time are vanishing. Large numbers are your silent bodyguards. They protect your world from atomic weirdness. And that, honestly, is the nicest thought in this whole topic. We live in a universe built from almost nothing, vibrating at absurd speeds, following quantum rules we can't see, and yet because there is so much of it in even a thin sheet of paper, the world shows up to us as calm, flat, warm, touchable, and repeatable. The atoms don't look like chairs, but a trillion of them, time averaged and space averaged, do. We've spent act after act proving that atoms live in a world 10 billion times smaller than yours, that they're mostly empty, that they only feel solid because they're in huge crowds. So now let's take the last big jump and see what happens when you keep stacking atoms not just into paper and hair and phones, but into mountains, oceans, and whole planets. Because Earth, this giant rocky ball we stand on, is nothing more than atomic scale repeated mindlessly over and over until it becomes geology. Start with a grain of sand. Earlier we said a grain of salt is about 5 million atoms across. Sand is bigger, so we're already way beyond that, into ridiculous counts of atoms just to make the smallest beach particle. Take a mountain, kilometers high, made of minerals that are themselves tight atomic lattices of silicon, oxygen, aluminum, iron. Every crystal in that rock is just atoms sitting 0.2 or 0.3 nanometers apart over and over in a pattern that never varies more than a tiny fraction of a nanometer. You can walk across a granite outcrop and it feels perfectly solid and continuous, but what you're really walking on is the same atomic spacing as in a tiny lab crystal, just multiplied until it becomes a landscape. Go bigger. Earth's radius is about 6,400 kilometers. If you divide that by 10 to the power of -10 meters, the width of an atom, you get a number so large it stops being intuitive. On the order of 10 to the power of 10 meters divided by 10 to the power of -10 meters equals 10 to the 20 atoms across if it were just atoms in a line. That's of course not how planets are built, but it gives you the sense of insult. We live on an object that is 20 orders of magnitude bigger than the things it is made from. And yet the rules that control the planet, why rocks are strong, why water flows, why air forms layers, why the core is molten, are still atomic rules playing out on a massive scale. Pressure at Earth's center? That's atoms being forced closer than they'd like, pushing back with their electron clouds, and gravity refusing to let them relax. The way seismic waves travel through the mantle. That's atoms and molecules passing vibrations along, exactly like sound in air, just at higher temperatures and pressures. Even the atmosphere's layering, why air gets thinner as you go up, is just the statistics of gas molecules under gravity, with each molecule still only a few atoms big. Look at it this way. If you could zoom all the way out until atoms were the size of marbles, your body would be bigger than a city, your house would be the size of a country, and Earth would be an unimaginable mosaic made from marbles packed together according to the same simple rules. Repel too close, attract at the right distance, stack to lower energy. Nothing new is introduced to make planets. It's just quantity. Stars? Same story, just hotter. The Sun is about 2 times 10 to the 30 kilograms of mostly hydrogen atoms, each one still around that 10 to the -10 meter size, smashed so close in the center that nuclear forces, the ones we met in the nucleus, take over and start fusing them. You get light, heat, life on Earth, all because a star is an atomic warehouse under high pressure. Even in space, where things look empty, the basic unit is still the atom. A nebula might have only a few atoms per cubic centimeter, but over light years that adds up to stars and planets. So when you think the actual scale of atoms compared to everyday things, Don't stop at the desk and the glass of water. Go all the way up. Your house, your city, your continent, your planet. All of it is just what 10 to the minus 10 meter units look like when gravity piles them up for billions of years. The gap between atom and ocean is enormous, yes, but it's a gap filled entirely by repetition, not by a new kind of matter. That's the beauty of it. The same boring, invisible, mostly empty building block makes clouds, cats, cars, continents, and cores. There's a funny mismatch in how we learn about the world. In school, and just growing up, we learn the big stuff first. Water boils at 100 degrees Celsius. Metals conduct. Glass is brittle. Air has pressure. Wood floats. Ice is cold. Sound moves faster in solids than in air. And only much later do we hear, by the way, everything you've ever touched is made from atoms that are mostly empty space. It feels backwards. Shouldn't we start with the atoms if they're the real thing? The reason we don't is the same reason this whole video is necessary. The atomic scale is too far below human experience to be obvious. You can't see 10 to the negative 10th meters. You can't feel a single atomic collision. You can't tell by taste that a sheet of paper is 1,000,000 atoms thick. Your senses stop reporting useful data long before the atomic world starts doing interesting work, so our brains build their physics of everyday life from the macro. I dropped it, it fell. I heated it, it boiled. I pushed it pushed back. That macro view isn't wrong, it's just averaged. All those smooth rules exist because of atoms, not instead of atoms. Pressure is millions of atomic hits. Temperature is billions of atomic jitters. Color is electrons jumping between atomic energy levels. Friction is tiny bumps of atoms scraping against each other. Even elasticity, the way a spring pulls back, is atoms being pulled apart slightly and then falling back toward their preferred spacing. We teach the macro first because it works for life. You can build bridges, cook food, make clothes, design cars, all on the strength of averaged out laws. You don't need to know the radius of a copper atom to wire a house. But if you want to know why copper wires work, or why glass is transparent, or why ice floats, or why some metals rust and some don't, you have to go down to the atomic scale and see what's actually being arranged. That's what we've been doing in this script. Taking things you already know and showing you the 10 to the minus 10 meter cores underneath. And once you've seen it, the world gets cleaner. You don't have to memorize that thin coatings can make glass hydrophobic. You know surfaces are only a few thousand atoms thick, so of course changing those atoms changes the behavior. You don't have to memorize that denser things feel heavier. You know we're packing more massive nuclei into the same atomic spacing. You don't have to memorize that we can't make transistors infinitely small. You know electrons will tunnel once barriers are only a few atoms wide. The macro world is like the user interface. The atomic world is the source code. Both matter, but one explains the other. And here's the best part. Even though you can't see an atom, you see the consequences of atoms every second. The shine on your mug in morning light, electrons in surface atoms reflecting certain wavelengths, the smell of food drifting through the house, molecules made of atoms diffusing through air, the softness of a blanket, fibers whose atoms can slide a bit before their electron clouds push back, the fact that you can breathe at all, air molecules spread out but numerous enough to deliver oxygen. Every ordinary, boring, daily thing is atomic in disguise. That's why the actual scale of atoms, compared to everyday things, is worth spelling out slowly. Once you know where the bottom is, and how small it really is, you can stop treating the world as if it's made from anonymous stuff, and start seeing it as layered, structured, and precise, even when it's just a piece of paper. We've taken the long way down tonight. We started at your scale, meters, millimeters, hairs, paper, and we kept slicing reality thinner and thinner until we hit the level where things stop being things and start being atoms, 10 billionths of a meter wide, mostly empty, held open by electric forces and quantum rules. And we saw the same pattern everywhere. Your paper is about 1 million atoms thick. Your hair is about 700,000 atoms across. A grain of salt is about 5 million atoms across. A single breath contains more molecules than there are stars in the observable universe. A single cell is hundreds of thousands of atoms across and is still full of smaller working parts. We saw that atoms themselves are stadiums of emptiness with a P in the middle, that you never actually touch anything because electron clouds refuse to overlap, that density is just heavier nuclei in the same tiny volume, that surfaces only a few thousand atoms thick can change how an entire object behaves, and that all the big rules we trust, pressure, temperature, solidity, color, are just what happens when you have so many atoms in one place that their random motion averages out into something calm. That's the real message behind the actual scale of atoms compared to everyday things. The gap between what you perceive and what exists is enormous, but it's bridged by repetition. Take a unit so small your eyes will never see it, repeat it 1 trillion times, and you get wood, water, metal, skin, mountains, planets. Take atoms that are mostly empty and pack them tight enough, and you get a table you can't push through. Take atoms that jiggle too fast to track, and put enough of them in a room, and you get air that behaves predictably. Take atoms with slightly different nuclei and scatter them through ice cores or bones, and you can tell the age of a glacier or a mummy. Our whole world is impossible if you look at one atom, too empty, too fuzzy, too small, but it becomes completely reliable once you look at crowds of them. So here's where we land. You live in a universe made of almost nothing, and it still works. It gives you solid floors, bright colors, breathable air, working phones, growing bodies, all from parts 1/10 of a nanometer wide. That should make the everyday feel a little more interesting, a little more precise, and maybe a little more relaxing. Because underneath the noise and weight and mess of life, the foundations are clean, mathematical, and steady. Thank you for listening, and good night.